lecture we continue the discussion on cell formation using sequence of parts. So, in the previous lecture we looked at this matrix where we have 6 rows for 6 machines and 8 parts, and the incidence data is given in the form of the sequence of visit of the machines. For example, part 1 visits machines 1, 3, 4 and 6, but in the order machine 1 first, followed by machine 6, then to machine 3 and then to machine 4. So, the 1, 2, 3, 4 would tell us the order in which each part visits the machine. We also saw the difference between an intercell move, particularly when we consider the sequence data, versus intercell move when we consider the binary data. For example, if for part 1 there is an intercell move, say on machine 6, if there is an intercell move and machine 6 belongs to some other cell, then there are actually 2 moves, because from 1 it has to go to 6 and then it has to come back. So, it will be treated as 2 moves, whereas when we used 0 1 data, only one element will be outside of the block, and therefore we would count it as one intercell move. So, the intercell move computation becomes different when we consider sequence data. So, we also saw some aspects of a mathematical formulation to solve this problem in the previous lecture. So, we define Cij to be the number of parts that visit machine j immediately after visiting machine I, or visiting machine I immediately after visiting machine j. Xij will be equal to 1 if I and j belong to the same group. Machines I and j belong to the same group. So, in this notation both I and j represent machines. So, Cij is the number of parts that visit both. More importantly, visit I immediately after visiting j, or visit j immediately after visiting machine I. If we consider this incidence matrix, particularly if we look at similarity between machines 5 and 6, parts 2, 3, 7 and 8, all of them visit both 5 and 6. Now, 2 visits 6 after visiting 5, so it contributes to the Cij. 3 visits 5 after visiting 6, so it contributes. 7 visits machine 6 after visiting immediately after visiting machine 5, so it contributes. And part 8 visits machine 5 immediately after visiting machine 6, so it contributes to the Cij. Whereas, if we take 1 and 4, machines 1 and 4, we would see that part 1 visits both machines 1 and 4, but it does not visit them immediately after visiting the other, therefore, it does not contribute to C14. Part 5 also visits both machines 1 and 4, but it does not contribute to C14 because it is not visiting immediately. Same with part 6. So, even though we have 3 parts that are common, the C14 will be 0 because there is no part that visits 4 immediately after visiting machine 1. Now, the formulation is to minimize double summation Cij into 1 minus Xij. Now, let us find out what we attempt to do by minimizing Cij into 1 minus Xij. Now, when we have a large Cij, it means we have machines I and j where a large number of parts visit I immediately after j or j immediately after I. So, it is desirable that I and j belong to the same group, because if I and j belong to different groups, then there will be 2 intercell moves for every Cij calculated. So, it is preferable that they belong to the same group. Now, Xij is equal to 1 if they belong to the same group. 1 minus Xij will become 1 if Xij is 0 and if they belong to different groups. So, Cij Xij into 2 will be the number of intercell moves that can happen when I and j belong to different groups. So, we want to minimize Cij into 1 minus Xij. So, the objective function essentially tries to minimize the intercell moves or tries to put machines that have large number of parts visiting them immediately after each other into the same cell. That is what it achieves to do. Here we have not fixed the number of cells. The formulation, none of the decision variables, Xij is the decision variable. Xij does not talk about the number of cells that we wish to create. There is no P or any such number which tells given input which tells us the number of cells. Therefore, we need to restrict the cell size so that we have a certain minimum number of cells. For example, if the number of machines is 6 and if the cell size is 4, then it will have 2 cells. So, one of the ways of creating more than one cell is by restricting the number of machines in a cell. Otherwise, it will lead us to a trivial solution where all the machines where there will be only one group, all the machines will be in that group, all the parts will be in that group and the intercell move will be 0. Now, we do not want that to happen, therefore, we restrict the cell size. So, the first constraint which is sigma I equal to 1 to k minus 1 xik plus sigma j equal to k plus 1 to m x kj is less than or equal to n minus 1 will restrict the number of machines in a cell. The other 3 constraints will ensure that if there are 2 machines I and j that belong to the same cell and if j and k belong to the same cell, then I and k should belong to the same cell. If I and j belong to the same cell, j and k belong to different cells, then I and k should belong to different cells, and so on. So, those are taken care of by those constraints and it is a binary formulation. So, when we apply this formulation to this data, we have not explicitly shown the Cij matrix. Cij is the number of parts that visit machines I and j consecutively, which means it visits j immediately after I or I immediately after j. So, we have not shown the computation of the Cij matrix. Now, when we try and solve this for the example that contains 6 machines and 8 parts, we have 15 variables and 63 constraints. 15 variables comes from Xij. There are 6 machines. So, 6 into 5 by 2. By 2 comes because the variables are defined as x12, 13, 14, 15, 16. 21 is not defined explicitly, 21 is the same as 12. So, 23, 24, 25, 26, x34, x35, x36, x45, x46 and x56. So, that gives us 15 variables, NC2 or MC2 if there are m machines. 63 constraints come from these sets of constraints that we have here. Now, there are 5 constraints that come from this and the rest of them come from here. So, it is a slightly large formulation in terms of number of constraints, particularly because of these 3 sets of constraints that come. This is given from I equal to 1 to m minus 2, j equal to I plus 1 to m minus 1, and k equal to j plus 1 to m for any I j k. So, in this case we will have I equal to 1 to m minus 2, which means I equal to 1 to 4, j will be for the corresponding I plus 1 to m, and k will be for the corresponding j plus 1 to m. So, this gives rise to a large number of constraints. So, there are 15 variables and 63 constraints, and when we solve this binary IP, we get the solution x13 equal to x34, x14 equal to x34, x25 equal to x26 equal to x56 equal to 1 with objective function 11. Now, keeping this solution, let us try and look at some of the aspects of this formulation. So, let us first write this solution. So, the solution will be x13, x14, x34, x25, x26, x56 equal to 1. So, the final block diagonal structure is shown here. So, we have 1, 3, 4, these are the machine groups. Now, we take part 1 visits machines 1, 3, 4 and 6. So, it will go to this part 1, 1, 3, 4 and 6. So, it will contribute to only one intercell move, because it will finish 1, 3, 4 in the first group. After that it moves to the second group. So, one intercell move. Part 2 visits 2, 5 and 6. So, part 2 does not involve any intercell move. Part 3 visits 5 and 6, they are in the same cell, does not involve an intercell move. Part 4 visits 1, 2 and 3. Part 4 will go here, but it first visits machine 6, then comes to 1 and 3. So, it starts here one intercell move to 1 and 3 and back. So, plus 1 intercell move. Part 5 visits 1, 4 and 5. So, part 5 will be here, but visits machine 1 first, machine 5 and then machine 4. So, machine 1, then machine 5 and then machine 4. So, creates 2 intercell moves. Part 6 visits 1, 2, 3, 4, 1, 2, 3, 4. So, creates 2 more intercell moves. Part 7 visits 2, 5 and 6. So, part 7 visits here and part 8 also visits here. So, with 6 intercell moves it has. Has 6 intercell moves. The objective function does not reflect the number of intercell moves. Objective function indirectly minimizes the number of intercell moves. The objective function happens to be 11 here. So, we need to explain this. The objective function is to minimize. So, objective function is to minimize Cij into 1 minus Xij. That is the objective function. So, when we expand this, this objective function will become C12 x12 plus C13 x13 plus C14 x14 plus C15 x15 plus C16 x16 C23 x23 C24 x24 actually it is C13 into 1 minus x13, sorry. So, all these will be written as 1 minus x12, 1 minus x13, 1 minus x14, 1 minus x15, 1 minus x16, 1 minus x23, C34 into 1 minus x34, so this is the objective function when expanded, there are 15 terms. Now from the solution we understand that x13, x14, x34 are 1. So this will be 0, 1 minus x13, x13, x14, x34 are 1. So these terms will become 0, 2 pi, 2 6 and 5 6, 2 5, 2 6 and 5 6 will go. So there are 9 terms in the objective function that will now contribute to the objective function. So in order to find the objective function value, we need to look at C12, C15, C16, C23, C24, C34, C35, C36, C45, one 5, 1 6, 2 3, 2 4, there is no C3 4, 4 5. So these are the things we have to compute. So these will add to the objective function. So we go back to the initial matrix. Now we see that C12. Now we need to check the number of parts between 1 and 2 that visit 4 6 is the one that comes here. So C12 we go back to the first 2 rows and we realize there is actually no part that visits 2 immediately after 1 or 1 immediately after 2. The only common part is 6, they do not visit. So this contribution is 0. We look at 2 3, there is only one common part which is 6. Once again it does not visit immediately after each other. So this also contributes to 0. So 2 4, there is one common part which is 6 again, and part 6 visits 2 immediately after visiting 4. Therefore C24 will contribute to 1. C15 we do not have a common part between 1 and 5. There is no common part, there is one common part between 1 and 5 which is part 5, and it visits 5 immediately after visiting 1. Therefore this contributes to 1. We look at 3 5, there is no common part between 3 and 5, therefore this will contribute to 0. We look at 1 and 6, part 1 is common, that will contribute 1, part 4 is common, that will contribute another 1, so 2. So 1 and 6 will have 2 contributions, so this will be 2. Three and 6, part 1 is a contribution, so it contributes 1, part 4 is common but does not contribute, so this contributes 1. 4 and 5, 4 and 5 have one contribution, part 5 is common between 4 and 5, and part 5 visits 4 immediately after visiting 5. So, the contribution is 1. 4 and 6, part 1 is common but does not contribute, and there is no other thing, so it is 0. So, the sum of these contributions is actually 6, 1 plus 1 2 plus 2 4 plus 1 5 plus 1 6, which actually gives us the number of intercell moves. So, this formulation essentially tries to minimize the number of intercell moves. Let us also try to understand the constraints and see how this solution satisfies all the constraints. So, the first constraint is sigma I equal to 1 to k minus 1, x I k plus j equal to I plus 1 to m x k j is less than or equal to n minus 1 for every k, equal to 1 to m, which means there are 6 machines in this formulation. I equal to 1 to k minus 1 x I k plus j equal to k plus 1 to m, j equal to k plus 1 to m x k j is less than or equal to n minus 1. So, there are m machines, there are 6 machines. So, there will be 6 constraints. So, let us take the first constraint and try to explain what actually happens. So, when k equal to 1, this is for every k equal to 1 to 6. Now, for k equal to 1, this term does not exist. So, only these terms will exist. So, for k equal to 1, it will become x 1 2 plus x 1 3 plus x 1 4 plus x 1 5 plus x 1 6 less than or equal to 2. So, this will ensure that if one of them, if one of the xij's happens to be taking the value 1. So, in our case x 1 3 took a value 1, which means 1 and 3 belong to the same group, and because I have a restriction of 3 machines, only one more can be added to this, and that can be either x 1 something or x 3 something. So, in this case 1 3 and then 1 4, so it became less than or equal to 2. It did not allow, for example, 1 3 1 4 and 1 5 to come into the solution, which means 4 machines would have been there. Therefore, this takes care of the fact that there can be a maximum of 3. We may have a situation that only 1 and 3 form a group, then the rest of them will take 0 and still this will be satisfied, less than or equal to 2 will be satisfied. Similarly, we can explain. For example, when k equal to 3, let us write just that equation for k equal to 3. So, I equal to 1 to k minus 1. So, it will be like x 1 is x 1 2, when k equal to 3, I equal to 1 to k minus 1 will be x 1 2 plus x 3 4 k plus 1 to m. So, when k equal to 3, it will become 4 x k j x 3 4 plus x3 5 plus x3 6 will be equal to 2. I think this should read I equal to 1 to k. I equal to 1, this becomes I, if when k equal to 3, x I equal to 1 to k equal to 3. So, I equal to 1 sigma I equal to 1 to 2. So, there are 2 terms. So, x 1 3 plus x 2 3 plus x 3 4 plus x 3 5 plus x 3 6 is less than or equal to 2. So, there have to be 5 terms in each constraint. Now, this will ensure that if 3 has been grouped with another machine which has a lower index than 3, that also comes into the picture, plus machines that are grouped with a higher index than 3. So, if we take this constraint and look at this solution, 1 3 is 1, 3 4 is 1. So, it satisfies with less than or equal to 2, which again indicates that 1 3 and 4 belong to the same group. This also satisfies that. So, similarly we can show that the first constraint ensures that the cell size is restricted to something. The next set of constraints we will just show through one instance. The next set of constraints, which are xij plus xik minus xjk less than or equal to 1, xij minus xik plus xjk less than or equal to 1, minus xij plus xik plus xjk less than or equal to 1. Now, let us try and explain this. Now, we want to show two or three things through these constraints. So, if x13 is 1, x14 is 1, then x34 has to be 1. So, x13 is 1, x14 is 1, this is x34. So, 1 plus 1 minus 1 is less than or equal to 1, 1 minus 1 plus 1, so it follows. Now, let us look at a case when this is 1 and this is 0. So, this will be 2 less than equal to 1 is not satisfied. So, automatically when these two is take 1, this one has to take a value 1 because xij is binary. So, this will force it to 1 and the other constraints will be satisfied. So, if xij and xjk are 1, then it will force xik to 1. Now, let us look at the other case. x13 is 1, x35 is 0. Therefore, it should force x15 also to 0. So, 1 plus 0, 1 plus 0, this should force x15 to 0. Now, from this constraint, whether this is 0 or 1, this is satisfied. So, 1 minus 0, 1 minus 0, which is 1. So, this will force xjk to 0, otherwise this will become 2. So, this constraint will take care of that. So, in a similar manner, this will also ensure finally that if xij is 0, if x15 is 0, x25 is 1. So, this will force x12 to 0. That will be taken care by the third constraint. So, these constraints put together for every ijk will ensure these conditions, that if xij is 1 and xjk is 1, then xik is 1 and so on. So, this is how this formulation works. Now, this formulation is very good in the sense that it provides an optimal solution. Its objective function value indicates the number of intercell moves. Now, the limitation of this model is that when we considered a matrix with 6 machines and 8 parts, we have 15 variables and 63 constraints. So, the number of constraints grows, particularly because the number of variables also increases, but the number of constraints grows because of the 3 constraints for every pair. So, what happens is, when we have a large number of machines, the number of constraints becomes very large. So, if it is possible to solve the binary IP and get the optimum solution, it is the best thing to happen. But if there are limitations because of problem size or because of solver availability and so on, then one has to resort to heuristic solutions, which are like similarity coefficient based solutions. So, researchers also proposed similarity coefficient based solutions to this problem. We have already seen 3 types of similarity coefficients. We have seen the Jaccard similarity coefficient, so for binary data we have seen the Jaccard similarity coefficient. We have seen a similarity coefficient which uses only the 1-1 pair, and then a similarity coefficient that uses both 1-1 pair and 0-0 pair, which you can call as similarity 2. This could be S1 and this could be S2. And we also saw that this is related to distance. Now, Nair and Narendran introduced a different kind of similarity coefficient between machines, where Sij is equal to Aij by Bij. Now, the very definition of Aij by Bij is very close to the Jaccard's similarity coefficient. Jaccard similarity coefficient had a numerator and a denominator. The numerator were represented the number of parts that visited both the machines. The denominator represented the number of parts that visited either one of the machines or both. Now, the new coefficient also has a numerator and a denominator with a very slight difference in the computation. So, the new coefficient is Aij by Bij. Aij represents the contribution of parts visiting both the machines I and j. So, numerator is similar to the numerator of the Jaccard similarity coefficient. The difference is part k visiting both I and j will contribute 1 if it visits the machine as its first or last machine in the sequence, and contributes 2 if it is an intermediate machine. So, let me read it again. Part k visiting both I and j will contribute 1 if it visits the machine as its first or last, if it visits one of the machines as the first or last machine in the sequence, and will contribute 2 if it visits both of them happen to be intermediate machines. Similarly, Bij represents the contribution of parts visiting either machine I or machine J or both. It contributes 1 if it visits the machine as its first or last machine in the sequence, and contributes 2 if it is an intermediate machine. The machine groups are formed based on the similarity values. So, the similarity coefficients are given here. So, let us try and explain the similarity coefficient. Now, this is the matrix. So, similarity coefficient between 1 and 2, if we take this, take the similarity coefficient between 1 and 2, there is only one part which visits both machines 1 and 2, which is part 6. Now, it visits 1 and 2 as the last machines, because the sequence of machine 1 is 1, sequence on machine 2 is 4. Therefore, it visits M1 as the first machine, M4 as the last machine. So, it should contribute 1. So, let us see what it does. So, now it contributes 1, this is common. So, it contributes 1 here because it visits as the first machine, and contributes another 1 here because it visits as the last machine. Therefore, it contributes 2, numerator contribution is 2, denominator is if it visits the machine either as either one of the machines or both the machines. So, if we take machines 1 and 2, parts 1, 2, 4, 5, 6, 7 and 8 visit them. So, this will contribute 1 because it is visiting as a first machine, this contributes another 1, this will contribute, it is visiting as an intermediate machine. So, this will contribute, so this contributes 1, this contributes 1, the denominator is 2 by 9. So, the contribution of the denominator is 9. So, let us go back and check 2 from here, 3, 4, 5, 7, 8 and 9. So, it contributes 1 because it is the first machine, 1 as the first machine, contributes 2 because it visits this as an intermediate one. So, 1 plus 1 2 plus 2 4 plus 1 5 plus 2 from the numerator 7, 1 8, 1 9. 1 contribution is 1 because it visits M2 as the first machine. So, the similarity coefficient is 2 by 9. Let us explain another similarity coefficient, say between 5 and 6. Let us compute between 5 and 6, the value is 11 by 16. S5 by 6 or S5 6 is equal to 11 by 16. Let us show the computation. So, we consider machines 5 and 6, the common parts are parts 2, 3, 7 and 8. So, part 2 will contribute 2 plus 1 3 because it visits machine 5 as an intermediate machine and machine 6 as the last machine. So, it will contribute 3. Part 3 visits machines 5 and 6, but visits only 5 and 6. So, visits 6 as the first machine and 5 as the last machine. So, it will contribute 2. 7 and 8 visit both of them. 7 visits machine 5 as an intermediate machine and 6 as a last machine. So, the contribution will be 2 plus 1 3, and part 8 will visit machine 6 as an intermediate machine because of the 2 and machine 5 as the last machine because of the 3, and it contributes another 2 plus 1 3. So, the numerator is 11. Now, the denominator is the numerator plus the contribution of parts that visit only one of them. So, denominator will be numerator 11 plus contribution from parts that visit either 5 or 6. That happens for part 1, part 4 and part 5. So, part 1 visits only machine 6, but visits as an intermediate machine, and therefore, it will contribute 2. Part 4 visits machine 6, but visits machine 6 as the first machine and will contribute 1. Part 5 visits machine 5, but visits as an intermediate machine and therefore, will contribute another 2. So, numerator is 11 and denominator is 16. So, this way we can compute the similarity coefficient matrix, which is now shown in this table. Now, from the similarity coefficient matrix, we will now try and get groups. So, the maximum similarity happens to be for 1 to 3, which is 9 by 10 is about 90%. 3 to 4 has less than that. 2 to 5 is also less, 2 to 6 is also less, 5 to 6 is also less. So, the maximum similarity happens for 1 and 3. So, 1 and 3 will come to the first group. So, 1 and 3 will form the first group. The next highest similarity happens for 7 by 9 is about less than 80%. 3 to 4 is 7 by 8, which is about 90%. 2 to 5 is 75%. So, 3 to 4 will be the next one with 7 by 8. So, 4 will join 3. The next maximum will be 2 to 5 is about 75%, 8 by 12. 5 to 6 is less than 70%, 2 to 6 is also less. So, 2 to 5 is the next highest. So, 2 to 5 will form another group, will form the second group, and we will add 6 to it. So, 2, 5, 6 will come here. Once again, the parts can be assigned based on the part assignment rule, and we get the same solution that we got for the integer programming formulation also. So, when we have a large sized matrix, one can use the similarity coefficient based approach to try and get machine cells, and then use the part assignment rule to assign parts and calculate intercell moves. Now, the similarity coefficient based method works on a simple idea that now we need to explain the idea as to how it is able to incorporate sequence data. One way by which we can show that it incorporates sequence data is by looking at the contributions to the numerator and to the denominator. So, there are parts that contribute 2 to either the numerator or the denominator, 2 plus 1. Earlier it was contributing only a 1 to a numerator or a denominator when we used only Jaccard's similarity coefficient. Now, we also need to understand how that 2 is going to help us. So, if we look at this matrix and let us say we look at 3 and 4, which had the we look at 1 and 3, which had the maximum similarity. If we look at 1 and 3, the ones that have maximum similarity, we would get let us compute the similarity for 1 and 3, or we can even show that let us say 5 and 6 actually belong to the same group. So, 2, 5 and 6. Let us show this 11 by 16 and how it helps. So, if we take 5 and 6, we realize that the higher value of the numerator came through the contributions of part 2, part 7 and part 8. All these parts contributed a 3, which meant that 5 and 6 are, particularly through this, they are visited as 2 consecutive machines. So, when you have 2 consecutive machines, their contribution will be large. The only case where 2 consecutive machines will have a contribution of 2 is from part 3. There are only 2 machines it visits, both happen to be 5 and 6, it contributes 2. If there were a part which visited 1, 5, 6 and 2 for example, then that would have contributed 4. So, what happens is when you have consecutive visits, even if one of the visit is the first or last visit, it is going to contribute 3. So, higher similarity coefficient indicates that there are more parts that actually visit these machines immediately after another. So, the bigger contribution actually comes from the numerator. The denominator also helps in its own way by kind of filtering the extent to which the values take, and also by ensuring that this ratio is between 0 and 1, because the numerator repeats itself in the denominator. The more significant contribution actually comes from the numerator. Now, this particular contribution where machines are visited continuously or consecutively or one after another, contributing to a higher similarity coefficient, is the same as Cij, minimizing Cij into 1 minus Xij, which was the objective function in the integer programming formulation of the problem. So, indirectly the similarity coefficient captures what the objective function captured in the optimization approach to solving the problem with sequence. Now, for the small sized problem that we have shown here through our example, the final solution is the same, where 1, 3 and 4 came to one cell, 2, 5 and 6 went to another cell. But for large problem instances where there are several intercell moves, it is possible to show that either the optimization approach that we saw now or the heuristic approach that uses similarity coefficients, we are able to get configurations with fewer intercell moves, particularly when we count an intercell move involving an intermediate visit as 2 intercell moves. Therefore, not only is the intercell move important, the intercell move for an intermediate machine, if it goes to another cell for an intermediate operation and then it comes back, then it is counted as 2 intercell moves, and indirectly it is also seen as a way of losing a little more control. If it were the first or the last operation, then you know that if it is a first operation in another cell, it is still not very desirable, but you would know that it enters the actual cell after completing an operation elsewhere, and once it comes in, we know that rest of the things are going to happen in this cell. So, to that extent it is fine. Therefore, 1 intercell move, and to that extent less control. If it finishes all the operations in one cell and has to go only for the last operation to another cell, even then certain amount of scheduling activities can be carried out in this cell such that all the work is done, control up to the point, up to the penultimate operation, and then it goes to another cell and then it leaves. To that extent there is some control, even though a little bit of control is lost. But if it has to go for an intermediate operation, then it actually affects in two ways, because the time at which the other machine is available and is willing to spare, certain activities have to be completed here, and depending on when it is coming back, the rest of the activities will also have to be scheduled. So, there are two physical intercell moves, that correspondingly the control is lost in two different points in time, therefore it is not very desirable. Therefore, higher penalty is given, and once that is the penalty is minimized, we now get machines which have consecutive operations carried in the same cell, which is the very purpose and spirit of cell formation, considering sequence of visits of the parts. The next thing that we will see is what happens when we consider cell load data, and how the cell formation problem changes when we consider cell load. This we will see in the next lecture.